Every iOS application operates in an environment where it must react to system-level events, like a repeating timer, modified file, or influx of network data. The common approach to monitoring these events is synchronous polling. In a polling model, your code enters a continuous loop, repeatedly checking the system to see if a specific state has changed. On the left side of this diagram, you can see the hardware cost of a polling loop. This constant querying consumes CPU cycles, leading to battery drain. There is also a structural constraint. Because the execution thread is occupied by the loop, other application operations are blocked until the loop finishes. iOS applications instead use an event-driven architecture, where the application waits for system notifications. Grand Central Dispatch, Apple's multi-threading API, provides a mechanism for this called a dispatch source. A dispatch source is an object designed to monitor system events and trigger a handler asynchronously. Structurally, it sits as an intermediary layer between your high-level application logic and the low-level OS kernel. The OS kernel handles the monitoring. When an event occurs, it sends a trigger through the dispatch source, initiating a single execution pulse in the application logic layer. This approach inverts the relationship. Instead of the code asking for updates, the system notifies the code only when an action is required. Operating system events are diverse. Traditionally, monitoring a network socket required different low-level APIs than monitoring a local file. Dispatch sources provide a single, consistent Swift abstraction layer. Diverse Darwin and Unix events are managed through a unified Grand Central Dispatch interface. GCD offers several specific types of dispatch sources, each categorized by the system events they monitor. Within this grid, .timer triggers at scheduled intervals. .signal monitors Yorence interrupts like sigint. .read watches file descriptors for incoming data, while .write notifies when they're writable. .process observes child process states. .mock receive receives mock messages for inter-process communication. Finally, .file system object monitors directories for modifications. Whether monitoring a complex Unix signal or a simple directory change, the underlying implementation pattern within GCD remains completely identical. This taxonomy simplifies kernel interactions, turning low-level monitoring into predictable Swift objects. We can see this pattern in practice by implementing the most common use case, the timer. These 4 lines of code establish a functional timer dispatch source. The first line handles object instantiation. Calling makeTimerSource allocates the monitoring object in memory. At this stage, the dispatch source is created in a suspended, dormant state. The second line configures the parameters for the event. The deadline parameter sets when the timer should first fire, in this case, immediately. The repeating parameter defines the interval, instructing the timer to trigger every 2 seconds. The third line uses setEventHandler to assign the work payload. This closure contains the logic that will execute when the event fires, here printing timer triggered to the console. When the 2-second interval is finally reached, GCD automatically and seamlessly dispatches this closure to a background execution queue. Because this handler is asynchronous, the main thread is never blocked while the timer is waiting to fire. The final line is the execution trigger, resume. This method is essential for the dispatch source to function. If a developer does not call resume, the source remains suspended, and the event handler will never execute. Calling resume signals the OS kernel to begin monitoring the parameters we defined. This lifecycle, instantiate, configure, attach, and resume, is the universal blueprint for managing system events through GCD. By zooming out to the system level, we can observe how this code impacts hardware performance. During the 2-second wait interval, CPU utilization rests at a near-zero baseline. Since the app isn't polling, the CPU remains idle or handles other tasks. When the kernel event fires at the 2-second mark, we see an immediate pulse in activity. The kernel notifies the dispatch source, which pushes the handle closure onto the GCD queue. The spike on the graph represents the execution of that specific closure. As soon as the closure finishes, the CPU utilization returns to its idle state until the next interval. Replacing continuous loops with these notifications reduces aggregate CPU usage across the application's lifecycle. This enables non-blocking, asynchronous handling of system events directly within existing GCD queues. By shifting the burden of monitoring to the kernel, dispatch sources allow an application to remain dormant until the exact moment an event requires execution.